So a wave essentially is a change in some property of a system away from equilibrium, and that change has to move through space. So for a one-dimensional system, we can essentially define that as some function whose argument is x plus or minus vt. And we'll find out the plus or minus determines the direction that it's moving. So essentially, we just need a function whose argument is x plus or minus vt for it to qualify as a wave. Now, it turns out that this wave satisfies the wave equation, which is given right here. The second derivative of y with respect to x is equal to 1 over the velocity squared times the second derivative of y with respect to t. This is essentially relating how this function changes in space to how it changes in time, and the constant that is tying those two properties together is the velocity. That makes sense. So let's go ahead and show that this definition of a wave is in fact something that satisfies that equation. In other words, when we use this as our y and we plug it into the left-hand side of the equation and take that derivative, and if we take the same function and plug it in for y over here, we'll find that the left-hand side is equal to the right-hand side. Now to do that, I'm going to have to make a change of variables, and so I'm going to define u as x plus or minus vt, and so then we can rewrite our function as y is equal to some f of u. Now just to note that the derivative of u with respect to x is just going to be 1, and the derivative of u with respect to t is going to be plus or minus v. And we'll make use of this in the next step. So for the spatial derivatives, we're taking dy dx. Now we have to use the derivatives here, and we're going to break this out as du by dx, d by du. That's my dy dx. And we noticed in the previous step that du dx was just 1, and so we're just left with dy dx is equal to dy du. Now we're actually looking for the second derivative, so we need to go ahead and do this twice. And so here we're taking one derivative, and then here's the second derivative. And again, notice that this term right here, du by dx, is 1. And so we have that d squared y dx squared is just the second derivative of y with respect to u. Now we need to do the same thing for the time derivatives. And let's just start off with dy by dt. And here we have du dt, d by du of y. Now notice that du dt we got up here as plus or minus v, and so this is what we get for dy dt. We're actually concerned with the second derivative, and so we're going to go ahead and differentiate twice, and each one of these du dt's gives me a factor of plus or minus v squared. Since it's squared, the sign doesn't matter, and so we're just left with the term v squared, d squared y du squared. Now let's go ahead and plug these things into the wave equation. The left-hand side of the equation, d squared y dx squared, gives me d squared y du squared from up here. Now if I'm going to look at the right-hand side of the wave equation, 1 over v squared d squared y dt squared, well, I've got my v squared right here. That's going to cancel out with this term right here, d squared y du squared. And sure enough, what we find is that we get the same thing on the left-hand side and the right-hand side of the equation. In other words, this wave equation is satisfied provided y is some function of x plus or minus vt. So this does in fact satisfy that wave equation. Anything that satisfies the wave equation is classified as a wave.